Identifying rotational symmetry and angles of rotation. For each figure below, determine if it has rotational symmetry. If it does, give the smallest angle of rotation needed for the figure to appear unmoved. Alright, so in this problem it only asks you to do 2 examples, but I'm going to do a few different examples so you kind of get the hang of it. What we're doing is we're thinking about this shape being rotated until to see if it will appear again. So one way you can think about this is with tracing paper. So if I take a piece of tracing paper here and I trace my object, what I want to do is see if I can rotate this object around my center there to see if it looks the same. So if I rotate this object around that center, if I go that far, my object looks the same again. If I do it again, I rotate again, boom, fills right in again. Okay? Now obviously this isn't perfect, but you can see that without going in a full circle, I can make my object appear unmoved or appear the same as it originally did. So what we want to think about, now that we know what's going on, is we want to think about that this right here is starting as the top. Okay? We're starting with a point on the top. And if we rotate it until this point is at the top, we rotate it up until that lines up with that one, my object will look the same. So we can do that with any of these vertices here. Okay, so here are all the points. I could rotate it 5 different ways and put that point at the top and it would look the same. So first what I want to think about is how many angles are in here. 1, 2, 3, 4. There's 5 equal angles because we can see that this is a regular polygon. Okay, so 5 equal angles. I know going in an entire circle is 360 degrees. So if I have 360 degrees to go all the way around, but I just want to think about a fifth of that, I'm going to divide 360 by 5, and I'm going to get 72 degrees. So each one of these angles in here is 72 degrees. So we saw that we could rotate it and it would look the same. So we knew it had rotational symmetry. Then my smallest angle is just 1 click over, which is 72 degrees. So for that one, that's it. So if your problem has regular polygons like these 2 examples, that's about it. You find your center of rotation and you think about how many angles that full circle is being divided up into. So here on this one, let's see if we can figure that out. So on this one, if I take this point and rotate it over here, it will look the same. So that's the angle I'm trying to find. Now, it's the same as all of these other angles, and we have 1, 2, 3, 4, 5, 6, 7, 8 angles. So I'm going to do 360 divided by 8. Okay? So if I get out my calculator and I do 360 divided by 8, I can see that each of those angles is a 45-degree angle. So it does have rotational symmetry, and it's 45 degrees. Okay? So if you have regular polygons, it's as simple as that. Now I'm going to do a couple of examples of non-regular polygons just to make sure you feel okay about this. So here's another example. This time, here's a regular polygon, so I'll whip through this one quickly. Okay, if I take this point and I rotate it till it hits the top over here, I know it will look the same, so it does have rotational symmetry. Okay, and I got to figure out the size of these angles, so I do 360 divided by the 3 angles on the inside, and I get that each one of these is 120 degrees. So my smallest angle of rotation is 120 degrees. Now this is the one that I want to talk about next because it's not a regular polygon, but we still need to think about the center of rotation. Now the point that I see that's facing straight up is like that, right there, okay? So if I rotate it till this point is straight up, so I rotate it from here up to the top, my image is going to look the same, and I could check that with tracing paper if I wanted. Okay, if I rotate till this point lands up here on top, then it looks the same. So I see the full 360, but divided into 1, 2, 3, 4 angles. So 360 divided by 4 is 90 degrees each. So each of these angles are 90 degrees. Okay, so it does have rotational symmetry, and the angle is 90 degrees. This one's harder because when we are doing regular polygons, we could just divide by the side number. But we don't want to count up the sides here and divide by that. We want to count up the angles there. Okay, and last example, just so that we're all clear, is this one. Okay, so I got to think about the center of rotation on this shape. And I want to picture this shape rotating to see if it will fill the same space. So I'm going to get my tracing paper again just to help you understand. Okay, I'm going to trace this object really quickly. Again, my tracings aren't perfect, but they're close enough to understand. Okay, so here's my shape, and there's my center of rotation. So if I line it right up, I want to see if I can rotate this object less than 360 and have it look the same. So far, nothing, 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 nothing. Nope, still not lining up, still not lining up, still not lining up. Boom. But I haven't gone all the way around yet. I could keep going, and that would be 360. So when I went halfway, it lined up. So this would have rotational symmetry, and the angle would be 180 because I know that's half of 360. Okay? Last but not least, we would check this last one. Find our center of rotation. Either picture it rotating or borrow some tracing paper from your teacher on your test, whatever you need to do. Let's rotate this. I'm going to mark the up this time. So this is how it started up. Okay? If I rotate, rotate, still not the same, 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 all the way around. It didn't line up until we got all the way back to where we started. So this one does not have rotational symmetry. And if it doesn't have rotational symmetry, it won't ask you for the angle. So there's an example of not rotational symmetry and a few irregular shapes.